Good morning, lecturer and fellow unisa students. My name is Maurice Leroux. I'm a student from unisa, and we were given an assignment for water infrastructure and resource management for the first semester of 2022. We were given a project to design a water supply system for the Chipese local municipality. The system was required for 4 townships that must be supplied by the Nanguingwa River. Each township was given its average daily demand in litre per second, as seen in the figure for the demands. Here in figure 3 we have a general layout for the water supply system, supplying from the river into the water treatment plant, from there going to the bulk storage reservoir. We have 3 junctions and we have our 4 demand centers. For the project we use the software Epanet, which is a design system for water. Epanet is also used to model water distribution systems. It sizes the new water infrastructure and it can investigate water problems or consisting water problems it can do. So for the method that we did, we first adjusted our notation in Epanet, displaying the node values and the link values. From there we started by adding the nodes as mentioned in the project report. It will run step by step through each step, adding the pipes. So first the nodes was created, which was your junction and your demand centers. Your tanks was applied, where you have 2 tanks, which is your water treatment plant and your bulk storage. After that, the reservoir, which is the Nanguingwa River, situated at the bottom as your source. Noted that the elevations that was given was all the reduced levels above sea level, but the river was, and the extraction works was to be taken as your datum. So all your elevations needed to be subtracted from 903. As you can see in yellow is the calculated values for the new elevations. After all the elevations are adjusted, the pipe length was adjusted also. Please note the diameters are still the default at 12 and not yet 300 as was proposed by unisa. So all the pipes from 1 to 9 linking the whole system, the length was adjusted. After that, a few settings and parameters was needed to be changed. We needed to set the times. We needed to make sure our flow units are in litre per second using the Hazard-Williams formula. Our time options that we needed was for a total duration of 3 days, equivalent to 72 hours, and we have a pattern time step of 4 hours. And after that we had to do the ratios for the period demand to average demand, which was given to us in the brief, and we had to do a pump curve with a flow of 600 and head of 80. After that we needed to adjust our storage tank with a diameter of 34 meter and a maximum height of 12 meter. And when all it was finished, the model was run with all the pipes being 300 millimeter. However, the design was not successful and negative pressures was received. As you can see, the head we experienced some negative, and the pressures, there are negative pressures in the network table from our nodes. So calculations was needed to make sure that we have the right pipe sizes. Therefore we used chapter 2 from our WRM notes. We first needed to design with the peak factors our average daily demands, and compiled it into the sketch, which will show all your values needed per pipeline. So that is the demand for the pipe, and manipulating the formula we calculated the required design diameters. After the design diameters was calculated, the whole system was adjusted by double clicking on each pipe and changing the diameter. The system was run again, this time successfully, and by going to your browser and your map, you could click on your nodes and links and get the required data that you want, meaning flow, pressure, head loss, as can see below. So our system was run successfully. With our system, the demand center 1 to 2 obviously was our smallest demand, being at 98 liters per second, but our pipe sizes in this model was taken the same as for demand 2, which was 105, which is a small increase. But to make the system more economic, the pipe size could have been changed to a 460 millimeter, which is 20 millimeters smaller than the one for the demand 2, over a 5.1 kilometer, which will make a difference in the feasibility for the design and more economic. And that is a small conclusion of what was done. The report will give more thorough results on all the tables and results obtained. Thank you very much.